Hi everyone, my name is Chang Shen from Gaoling School of Artificial Intelligence, Renmin University of China, and I'm excited to present our latest research, Paragon, parameter generation for controllable multitask recommendation. We all know that recommender systems face a major challenge. User preferences and platform needs change dynamically. So how can we adapt a live model to these new requirements without costly retraining? This is the core problem we will address today. Please take a look at this slide. On the top, we see the traditional approach, which we call the static paradigm. We train a model with a fixed objective, like 70% accuracy or 30% diversity. Once deployed, it sticks to that goal. But the real world is dynamic. As the bottom diagram shows, when a new task requirement emerges, such as a Black Friday event, we are forced to retrain the entire model. This process is expensive and slow, failing to meet the need for real-time adaptation. Thus, we proposed CMTR, that is, Controllable Multitask Recommendation Framework. The key idea is to create a framework where we can input a new task requirement and instantly generate a new model that meets the task requirement. To categorize our approach, let's look at this slide. There are generally three ways to control a recommendation model: pre-processing, which adjusts the input; post-processing, which reranks the output; and in-processing, which modifies the model itself. Paragon is a form of in-processing control. We don't change the user data, nor do we simply reorder the final list. Instead, we intervene directly on the model's parameters to adapt its core logic. To achieve this, we designed Paragon. Its workflow, as shown in this diagram, is divided into three core stages. Stage 1, preparation of adapters. Instead of generating an entire massive model, we focus on generating a lightweight adapter. As you see on the left, we split the model into a fixed backbone for foundation ability and a trainable adapter. We then train a set of adapters for various task requirements, such as 90% accuracy and 10% diversity. These adapters serve as the training data for our generator. Stage 2, training the parameter generation model. Now, we have optimal adapters for different task requirements. We train a model to learn the mapping between them. As shown in the middle section, we use a powerful diffusion model. We treat each adapter's parameters as an image, and we treat the task requirement, that is the weight for accuracy and the diversity, as condition. The model learns to generate high-performing adapter parameters from random noise, guided by this condition. Stage 3, test time parameter generation. This is where the magic happens. As shown on the right, when a new task requirement arrives in the online system, we feed it as a condition to our trained generator. Instantly, it generates a new adapter. We then combine this new adapter with the backbone to form a new recommendation model, all without any retraining. So, how well does Paragon perform? This table shows a comparison with several baseline methods. In short, average hypervolume measures overall performance. The Pearson correlation measures controllability. As you can see, Paragon consistently ranks at the top across all datasets, achieving performance comparable to the costly retrain approach. These curves provide a more direct look at Paragon's controllability. The x-axis is the accuracy weight, and the y-axis shows performance. The solid blue line represents the optimal retrain result. Notice how the red Paragon curve closely tracks the blue line. As we increase the accuracy weight, the model controllably delivers high accuracy, while diversity decreases, just as expected. Paragon's ability extends beyond just accuracy and diversity. We introduced fairness as a third control objective. The results show that when we give the fire command, the model's fairness is significantly better than that with the unfire command, without hurting the other metrics. This demonstrates the scalability of Paragon to more complex, multi-objective scenarios. Of course, efficiency is our key advantage. This table compares the time it takes to generate a new model. Retrain can take several hundred seconds, while Paragon takes only about 2.5 seconds. This is a speed increase of at least 90%, enabling true real-time response. Finally, a quick case study. When the accuracy weight is low, such as 0.1, the recommendation list is highly diverse in the categories. When the weight is high, such as 0.9, the list ranks the target item at the top one. This clearly shows the controllability of Paragon. To conclude, we introduced Paragon, a novel parameter generation framework for multitask recommendation. By generating lightweight model adapters on the fly, Paragon provides a practical solution for real-time, customizable recommendation, which reducing computational costs. Thank you for your attention, and I'm happy to answer any questions.
Thanks for the presentation. Excellent work. Now that we're supposed to do controllable recommender systems, as we've been presenting a few talks ago, we need to understand how the algorithms can produce desired mixture of parameters. But the question is, to what extent would we produce really correspond to user expectation and how we can evaluate it? You get very nice automatic data-driven evaluation, which shows kind of more diverse. But again, as the previous talk shows, diversity is the eye of the beholder. The system diversity measure might be different for user diversity measure. So the question, how you would evaluate that your controllable generation achieved the results in the eyes of the user, not only just by data evaluation. Do you plan to run like A/B testing study or something like that to confirm that you're achieving your goal? Too much, right?
Okay. Let me check the question. You say you want to ask the control is user side or platform side.
Yeah, I think the question was, so you say that your system now can better adapt to diversity as an optimization strategy, so you don't need to do retraining, but in the end, is that what the users want?
The diversity assessment isn't that of the user. User thinks it's diverse or not, right? So how we can really evaluate from the user point of view that your system indeed do exact diversity or exact popularity as you're trying to achieve, right?
Okay, maybe you can email me at another time. Sorry.
The examples you showed were not clear enough for me. So can you give an example of a dynamic environment where we need to change the task online?
Okay. An example. For example, in some scenarios, the platform needs to pay more attention on the diversity of the recommender systems, but the situation is very sudden and need instant result. So we don't have time to retrain the model. We just input the new weight on the generator, so we can get a new recommendation model. This is very This is very fast. It's very okay. Any question?
Yeah, I mean, so there's a follow-up question, I think, also in the chat, if I may. So somebody asks in the chat, it seems that post-processing would be even more time efficient. Did you compare your technique against post-processing alternatives?
The post, yes, the one of the baseline is post processing. The MMR is the post processing baselines, and we found there are some bad performance in this baseline, such as such as the MMR baselines is away from the optimal performance. That the optimal performance we defined as the retrain methods. Yeah.